Okay, so the James Webb Telescope, is that Hubble 2.0?
Yeah, I think it's fair to say it's Hubble 2.0. So here's, let me just explain for your listeners or remind them that we are in what we call a Big Bang cosmology, which means that the universe is expanding. And it's been expanding since its very earliest creation as far as we can tell. We have a lot of evidence that that's true, all the way back to a tiny fraction of a second up to more than 13 billion years, the universe has been expanding. Now, because of that, and because of the way that general relativity posits light that's embedded within the universe, if you have like a photon that's been emitted from a distant galaxy and it's streaming toward you, as the universe expands, it expands in proportion. Its wavelength gets bigger. So if you look at very distant objects, because the universe has expanded by quite a factor between the time the light was emitted and the time it gets to you, that light has expanded too, and that means it gets redder. Longer wavelengths are redder wavelengths, and that it gives rise to what's called the redshift. And the redshift is a very common term in astronomy, and redshifted light just means that the light has undergone an expansion of its wavelength between the time it was emitted and the time it hit you, okay? Now, as you look farther and farther back, of course, the universe has expanded by a bigger and bigger factor. And so ordinary light that we see, maybe half a micron, half of a millionth of a meter in wavelength. If we look back to when the universe was half the current age, it's expanded by a factor of 2, that light is about twice as long in wavelength, right? So it goes from half a micron to a micron. If you want to look back all the way to when galaxies were first created, the universe since then has expanded by a factor of between 15 and 20, according to our best estimates. So that means that ordinary light that we see at half a micron, if it's expanded by a factor of 20, it now has a wavelength of 10 microns. And 10 microns you can't see. That's in what's called the thermal infrared. And so you need special detectors and special telescopes to be able to detect that light. And that's what James Webb is designed to do. It's a telescope which is large, and it's cooled because anything warm will emit light at those wavelengths. And it's going to be extraordinarily sensitive to light which has been shifted by factors of 20 or even more from the time it was emitted. And so James Webb was designed specifically to be able to look back to the very earliest times in the universe when the first galaxies were being assembled, if you like, out of the sort of soup and detritus of the Big Bang.
Have we gotten any images back from it?
We have. They are just spectacular. It's creating this telescope and then aligning it and making the images good was probably one of the biggest technical challenges that astronomy has ever faced. And the reports are that they've actually done it better than the specifications, that the telescope is delivering much better images than people had expected it to deliver based on their estimates of how hard it was to align.